What's going on, smart people? There are a lot of terms and concepts that you encounter for the first time in physics, and then they just end up following you through the rest of your physics career. And at least for me, it can be difficult to tell if I really understand them or if I just gotten used to them over time. And one prime example is the concept of a cross-section. And unfortunately, there's two ways that the term cross-section is used. In the cross-sectional area, which is more geometric in nature, and the cross-section as defined in scattering experiments for, say, nuclear and particle physics. Now, in the next video, we'll be focusing on the cross-section and more specifically the differential cross-section, but the highlight of this video is going to be on the cross-sectional area. Now, at first it may sound like it doesn't warrant an entire video because it's pretty easy to picture. You have an object, you slice it a certain way, it's the area of that slice. Like if you have a loaf of bread, it would be the area of the slice of bread. Or if we had a spherical ball, it would be the pi r squared of the ball, the cross-sectional area. The issue is not how to picture this stuff in our mind, but rather how can we describe it using the tools we have and what we can measure in, say, a scattering experiment. And the first thing is, well, why would a scattering experiment tell us anything about the size of an object in the first place? Well, the first way that I think is a helpful way of thinking about this is, let's say that we have a little ball here, and we're shining a light on the ball. We're interested in understanding the size of this ball. Well, one thing that we can do is if we shine our light on the ball, it's going to cast a shadow onto the surface. Shadow here. Let's pretend like that's a perfect circle. Now the area of the shadow, which is going to be circular, is going to be the cross-sectional area of this ball. We didn't actually have to cut it in half. We can just look at its projection onto the surface. Now classically that's what we would do with maybe like a big beach ball or something like that. For subatomic particles, that's not very practical. But one thing that we can do is we can understand the properties of the light that we're shining initially. In other words, if we know how much light there is, and we know how much light is blocked off, then we can relate this ratio of scattered light due to the object being in the way to the incident light, the light that we had to work with in the first place, to this shadow, this cross-sectional area that we're interested in. So in this little cartoon drawing, we can see that it's kind of related, but we'll put it into more formal definitions in just a bit. Now, to give you a bit of a timeline for this video, we're going to start with one particle. We're going to have a beam of particles that is hitting one target, and we're going to uncover what the cross-section is. Then we're going to generalize this to having a sheet of targets to make this a little bit more realistic. And then finally, we'll touch briefly on the idea of a differential cross-section, and then we'll talk about interpretations and the limitations of these interpretations. Okay, so let's go ahead and draw our beam of particles hitting one target. So we have our little beam that's parallel. In principle, when I drew that light, that shouldn't have been coming from a single point. It probably should have all been parallel, but you get the idea. So we have a beam of particles that is hitting a target that is smaller than the cross-sectional area of the beam itself. Okay, so here's our little target, and here's our beam of particles. Why should it be smaller? Well, if we want to understand the size of the beach ball, but we shine a laser pointer at it, we're not going to see a real shadow in the first place. There's no light that's going to be around it. So the size of the beam should be larger than the size of the object initially, okay? So let's go ahead and say that this little cylindrical beam of particles has some cross-sectional area that I'm going to call AB. And the cross-sectional area for the target, I'm just going to call sigma. That's the typical notation that we use. We always use sigma. Let's also say that the beam has a density, a beam density, or let's call it a number density that I'm going to say is NVB. V to stand for volume. I'm making the distinction here because once we move on to multiple targets, the surface density ends up popping up more. So this is just minimizing the action on my end. We'll use surface densities and volume densities. So the index V is the volume number density for the beam. Okay, so that has that density, and we want to be able to relate this stuff to the cross-sectional area. We're going to have a certain number of particles scattering off of this target. Let me go ahead and make the target a little bit smaller just to make it clear that it is smaller. There we go. There we go. There's our happy little target. All right, how do we define this cross-section? The way that we're going to do it is by direct analogy with something that is like the first problem you solve in what's called Monte Carlo numerical methods. So as an aside, we're going to do something a bit similar and kind of have a dictionary connecting the dots between them. So one really popular problem to solve in what's called Monte Carlo, if you haven't heard that before, just bear with me. is you want to calculate what pi is numerically. So one way that they do that is you take a circle and you put it inside of a square. Okay. There we go. There's our circle and our square. And this will make sense in just a bit. I get that this seems like a completely different problem at first. So the circle, we're going to say, has a radius r, which means that the square will have a length and width 2r. So the area of the circle is pi r squared, and the area of the square is going to be 2r times 2r, which is going to be 4r squared. Then what you do is you take the ratio. We say that the area of the circle divided by the area of the square is equal to, the r's cancel, and we get pi over 4, or pi is equal to 4 times the area of the circle divided by the area of the square. Let's see if this makes sense. Well, most of the circle takes up most of the area, or the circle takes up most of the area of the square. So this ratio should be less than 1, but probably pretty close. So we get that something is, pi is a little bit less than 4. So that's a pretty okay first approximation, just looking at it pictorially. But this isn't very helpful at all, because we already know that pi is in terms of this area of the circle, but we don't know what pi is, so it's kind of circular. Not circular, but it's not helpful. So one thing that we want to do is we want to express this ratio in a way that we can actually work with. And the way that we do that is by first discretizing the space. So we slap this whole thing on a grid. Okay. Let's go ahead and have a bunch of little grid lines. Okay. And all of these little squares, though it may not look like it here because of the drawing, all of these little squares will have the same area. So the area of the square is just going to be the total number of these little squares times the area of these little squares. So we'll let the area of the little squares just be little a. So the area of the squares is just the number of the squares times a. And we can approximate the area of the circle as the number of squares that are inside of the circle times a. So I'll write that as NCI times a. So if we take the ratio of these two as an approximation, which gets better as we introduce more and more grids, little grid spaces, we can express this ratio as the ratio of numbers of squares that are in the circle versus the total number. So it's equal to 4 NCI over n. Maybe a little approximation here. Now, if you'd like to see this put into action, I've made a video calculating pi explicitly this way in Python, which is kind of cool. But the main idea is it would be incredibly inefficient to actually use every single one of these squares, especially if our problems move on to multiple dimensions. This is just calculating pi, but maybe we would do something else in higher dimensions, in which case all of these grid lines would grow exponentially, right? So the idea behind Monte Carlo is that instead of using every single space here, we randomly sample from it. It's kind of like if instead of using every grid, we were throwing darts randomly at this board, where the darts are guaranteed to land somewhere in the square, but not necessarily in the circle. Okay, so in that sense, as we use more and more darts and we increase the number of random samples, it'll approach the average. Right, so we end up replacing the number of circles, the number of squares in the circles, with the number of darts thrown that landed in the circle, divided by the total of number of darts thrown. Okay, so NCI becomes darts hitting circle, say number of darts, and N is the number of darts thrown. So this becomes more statistical. We're not using every single grid line in the grid. We're using a random distribution of them. Okay. Now if we turn this problem, if we go back to this and we kind of turn it on its side, maybe you can connect the dots between what's so similar out of these problems. Here, instead of darts, we have a beam of particles. And instead of a circle in a square, we have, well, it would be like a circle in a larger circle. So if we turn this problem over, we have our particle beam that has some radius and our target that's on the inside. So let's see if we can kind of map definitions here. The area of the circle is then replaced with the cross-sectional area of our target. So ACI is our sigma. The area of the square is the cross-sectional area of our beam. Okay, and NCI, the number of darts that landed in the circle, is replaced with the number of beam particles that overlapped with our target. So it's the number of beam particles that are within this radius here. But if it's within this radius of the target, it's in the way. And if it's in the way, it's going to scatter classically, right? So we can replace the number of particles that's within the circle with the number of particles that is being scattered. So NCI gets replaced with the number of particles scattered, and N can maybe just stay the same. It's the total number of beam particles. Okay, so we identified the ratio of areas with the ratio of numbers. So we have that the ratio of numbers, we called that sigma, sorry. So sigma over the beam area is equal to the ratio of numbers, ns, divided by n. And we can express this total number of particles in the beam in terms of a beam density, right? The beam density, NVB, is just the total number of particles in the beam divided by the volume that it's enclosed by, which is equal to, actually let's just use that. So this is equal to NS divided by NVB times the volume, which is equal to NS NVB times volume of a cylinder is just its cross-sectional area times the length. So it's just the cross-sectional area of the cylinder times the distance traveled by the beam. And lastly, we can express that distance traveled as the velocity of the beam particles times the time of the experiment, which is equal to NS over NVB times AB times velocity times time. Now, one thing that we define is the flux. The flux is defined by the number density, the volumetric number density, times the velocity. This is just flux. Okay? And these areas end up canceling. So we get that the cross-section for a single target is equal to the number of scattering events divided by the flux of the beam times the time of the experiment. Nice and simple expression. We'll talk about this more once we go to the sheet of particles, but what's kind of annoying about this is some of this is a property of the beam, but the property of the beam is also related to the thing that's being measured, so you can't really treat them as independent variables. Like if we increased maybe the flux of particles, then maybe the number of scattering events would increase. So you can't say that the size of the object will decrease if I increase the flux, because that is related to the number of scattering events, right? Yeah, so, or especially for if we have a density of particles. There may be some wiggle room there in the fact that we're considering that you can't have more than one collision at a time. So, but anyway, so that's the cross-sectional area. That means that if we count the number of particles that are scattered, we understand our beam very well, we understand the flux of incident beam particles, and the time of the experiment. We know the size of our object more or less. Now we'll talk about the limitations in this way of thinking not very soon, but towards the end of this video. But as for now, that's how, in the context of billiard balls hitting billiard balls, that's how we can think of these things. Now let's go ahead and move on to if instead of having one target, we make it a bit more realistic and we have a sheet of targets, like a gold foil experiment. And this is going to be why this video took a couple more days to put out, because I actually had to think about this quite a bit more. So if you don't care about the generalization, you just wanted to get an idea of the cross-section, you can go ahead and skip to this part of the video. But understanding that the generalization is, we're doing it because it's more important, because it's more realistic, that you might want to sit through it. And you might want to see what I struggled with in making this video. So I'm going to go ahead and erase this stuff. And we're going to denote this as single particle, single target. And now we're going to move on to the multi-target. Now for a multi-target, we're going to have a beam that's directed at a sheet, and the total area of that sheet will be larger probably than the area of the beam, but that's not the same as what I was saying earlier. The target is still the same size and is smaller than the beam. We just have a lot of targets now. Okay, so let me go ahead and erase this stuff. I'll draw my little partition. I'm going to erase this stuff too. So if you see a subscript V, that means volume. If you don't see a subscript, you can assume that that means surface number density. And I'll reiterate that a couple times because I like beating dead horses. Okay, so let's go ahead and partition this off. And now we're going to look at multi-target. Multi-target. And we're going to be pretty careful with the assumptions that we're making. We're going to be liberal with making assumptions, don't get me wrong, but I'll tell you when we do. So now we have a beam of particles that is directed at a slab of target. Slab's not the right word. It's going to be very, very thin, okay? So we have our beam of particles with some cross-sectional area AB directed at some sheet of targets. So we got these guys. Oh wow, I should have chosen a smaller slab. All right, the first thing is that we're going to denote, this is a sheet of targets, so it's going to have some number density that is a surface number density. It doesn't have any width to it, it's just, or depth to it, it's just a sheet. So we're going to go ahead and say that the number density is going to be the number density of the targets. No subscript means that it is a surface density in this case. Okay, and we're also going to talk about if we take a slice of our beam at a certain time, that's going to have a certain density of the beam particles. So this will have some surface density NB. Again, different from this. This is volume, this is surface. Last time I'm saying that. A nice way of picturing this, and it's going to help us lay out the assumptions that we're making in this problem, is we're going to throw this on a grid right away. But the first thing is that this beam of particles is only going to know anything about the particles that are within this cross-sectional area AB. It can only interact with particles in this circle, right? It doesn't know anything about these ones. The particles are only going to interact with these because they're billiard balls, right? At least in this case. So let's go ahead and throw this on a grid. We're going to pretend that it's a spherical beam. Okay. And the shaded regions of this grid are going to be where the targets are. Okay. Here's a target, here's a target, here's a target. Okay. So the total area here is going to be the cross-sectional area of the beam. And we're going to be interested in not the little areas here. We already know that they're the cross-sectional areas of the target. That's the area that this is blocking off. The area taken up out of by all of the targets out of the available area, I'm going to call A sub t. So A sub t is the area blocked off by these targets, which is just going to equal the number of targets times their cross-sectional area. It's the number of targets times their cross-sectional area. Okay? And now I'm going to lay out some assumptions here. Assumption number one, which is a big one. We're going to assume that the beam is uniformly distributed and very dense. Now, the beam being uniformly distributed honestly is not a very realistic assumption to make. Typically it won't be. It'll vary with the distance. That's a detail of the beam, not of the cross-section itself. So we're going to be looking at an idealized case here. Sue me, okay? So we're going to assume that we have a uniform distribution of beam particles, and it's very dense. This is a very key part here. Uniformly distributed could mean that I have maybe a particle here, 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 and here. Each one of these has one space in between them. But if we look at it this way, we can be missing certain targets though this way. So uniformly distributed and very dense allows us to say that for each one of these squares, we have a beam particle as well. In other words, if there is a target blocking out area, it is guaranteed to be hit by one of our beam particles. That's one of the assumptions that we're making. Okay, the second assumption is that only two particle collisions at a time. Okay, we're not going to be colliding two beam particles with one target. What that would look like, I'll erase it right away, but it'd be like if we have, if our target took up multiple squares, so multiple beam particles would hit the target. We're eliminating that from discussion, which isn't actually as unpractical as the first one, because you can always choose a slice of time resolved enough to where, oh, now we see that the other particle lagged behind a little bit. So this one actually isn't crazy, but that's one of the assumptions that we're making. Okay, if under these assumptions, then the area AB is equal to the number of beam particles here, which I'm going to index it with an NB, and we'll talk about what this is in a bit, which was a big source of my confusion earlier this week, times the cross-sectional area again. Now this number of beam particles is not the total number of beam particles. This is not n. This is the number of beam particles on that cross-sectional area of the beam. Okay? Now, so this is like a number, this is a number on the surface, not the number in the entire volume. Now this number of target particles we can express in terms of how many particles there are in the area that it's enclosed by. So this is the number density, which I'm going to call n sub t, times the area enclosing it, a sub b, times sigma. Okay? Now if we do what we did last time, we take a ratio, we get that the area of the target divided by AB is equal to NT over NB, which is equal to, I mean, these areas cancel, so we get NT times sigma. So it's starting to look pretty close, only in terms of a number density as well. We have a ratio of numbers and we have a number density to the previous case. But the big difference, and this was the thing that took me a while, admittedly, to reconcile, is that this is not a number of particles that is being scattered, and this is not a total number of particles in the beam. This is a number of targets, and this is a number of particles on the surface, the cross-sectional area of the beam. So the goal now is how can we relate those to number of events, number of scatterings, and the total number in the beam. Well, the way that we can do that is that at any slice in time, we will have exactly NB particles, okay? At any slice in time, we have NB particles, and in this surface area, if the square is in the way, it is going to be hit, right? A particle is going to be hit. So the number of targets at any slice in time should be equal to the number of scattering events. The number of scatterings will increase with time because if it remains intact, we're going to keep directing beam particles at it, so the number of scatterings is going to continue. But the number of scatterings at a certain slice in time should be equal to the number of targets, because we're not allowing for more than two particle collisions, and we're guaranteeing that there's at least, or that there is one beam per little box here. Okay? So how do we phrase that mathematically? Well, if we want to talk about a specific slice in time, we have to have a prior and then following slice in time, which we'll characterize by some number tau. So what I'm saying here is that at a certain slice in time, the number of scattering events is equal to the number of targets. So ns, which is going to be the number of scatterings as a function of time, minus, actually let me do a step forward in time first, of t plus tau minus ns of t should be equal to the number of targets. This is saying this is the width of our slice in time. This is our window. If we have a continuous beam, maybe substitute tau for d tau, but this is our slice. So we're looking at our beam now, and then a little bit in the future, and we're looking at how many scattering events took place in that little window, that little slice in time. Okay? Well, if our beam is traveling at a constant velocity, then the number of scattering events should probably increase linearly with time, right? So we can say that the number of scattering events at t equal to 0, we say that the beam has already reached the target. So we say that it's at least equal to the number of targets, 1 plus some we know that it should be linear in time, parameterized by our time step. T over tau, because it should be dimensionless, so that both of these are dimensionless, okay? And let's see if this makes sense. So if we do ns of t plus tau, so let's go ahead and substitute that in here. So that's going to be n sub t 1 plus, t is now substituted for t plus tau over tau, minus n sub s of t, which is minus n sub t 1 plus t over tau. That's equal to n sub t plus n sub t over tau plus tau over tau is 1, so that's plus n sub t minus n sub t minus n sub t over tau. These guys cancel. One of these factors of n sub t cancel, so we get what we expected, that the number of scattering events in this little time slice should be equal to the number of targets at any slice in time. Okay, so we're going to hold on to this. So now we have a relationship between the number of events and the number of targets. And we can actually do the exact same thing. I'm going to erase this for the sake of board space. We can do the exact same thing relating the surface number of particles in the beam to the total number of particles in the beam. Okay, so similarly, we would have that the total number of particles in the beam should be equal to the number on the surface, 1 plus t over tau. Okay, why this? Well, if we assume that let's also just write that here, constant velocity beam. The reason that we can do this is, for one, we're assuming that the distribution of beam particles is uniform and the beam is traveling at a constant beam velocity. So if it increased anything but linearly, that would correspond to the beam density either increasing or decreasing, right? But we're already assuming that it's uniformly distributed, and we're assuming that it's constant, so this should also grow linearly with the number of particles on the surface of the beam. So when we take the ratio of these two, we see that the number of targets divided by the number of beam particles, well, the time dependence actually cancels, and we get that this is equal to the number of scattering events divided by the total number of particles in the beam. Now, if we took into account that the beam accelerates or whatever, if we knew that it was parameterized by some other way in terms of time, well, that's fine. We would just multiply it by some other functional dependence of time, and they would still end up canceling. The key thing is that the time dependence for both of these should be the same, regardless of if it's linear or not. These two should match. So when we consider that, then we get that the ratios are equal, and we can substitute this in, so we get that the number of scattering events divided by the number of particles, the total number of particles, is equal to the surface number density of the target times the cross-sectional area. In other words, the cross-sectional area is equal to 1 over the number density times the ratio of these number of events to total number, which is equal to ns divided by nt. Let's go ahead and expand this guy again. So this is going to be a volume density, nvb, times the volume, which is the area of the beam, times its distance, which is the velocity times time again. So all I did was expand this guy. Okay, so we've got our flux. So we've got ns divided by nt AB times the flux times time. And this is our expression for the cross-sectional area if we have multiple targets in a sheet. Now let's see. So this is the number of target particles per unit cross-sectional area of the beam. If we have one particle in that cross-sectional area, Then we have 1 per AB, so the AB's cancel, and we get just a 1 here, and this reduces to the single particle target. So that's a nice little check that we're doing everything correct here. I hope you can maybe see why this took me so much longer to think about conceptually and to make it more formal, because everything online when it comes to this takes more of a why derive something when defining it to be the case is just as good. You know, so this took me a while, but I hope this sheds some light on everything. One big takeaway from all of this is how misleading the equation for the cross-section can really be, because we're used to seeing variables in equation as independent from each other, but that's just not the case here. You're tempted to say that, oh, if I increase the density of targets, does that mean that the size of the target individually decreases? The actual object size is changing just because I put it next to more? No, you can't really treat those independently, because if we increase the number of targets, again, we'd also be increasing probably the number of scatterings. So things like these are coupled together, but you can't change them independently. Not to mention, one you can actually manipulate experimentally, the other you would have to measure. You're not really free to choose how many scatterings there are going to be, especially in the real world when interactions happen at a distance and are more probabilistic. Okay, so we've talked about this. Next, we're going to just move on very briefly into the concept of what's known as the differential cross-section. For those of you who skipped the part of the multi-target, well, welcome to, I guess, the end of the video. I didn't expect it to take so long. So now that we've defined the cross-section, we understand it to tell us about the size of the object. One thing that's very common to do is to express this cross-section as a summation of little infinitesimal cross-sections, as an integral of little infinitesimal cross-sections, which will oftentimes be expressed as the integral of d sigma d omega, where omega is the solid angle that the particle is scattered into. So we take into account where it's being scattered into. Then the definition, we define the differential cross-section of theta is defined to be d sigma over d omega. It's called a differential cross-section. It's terrible nomenclature, it's just persisted over the years. This isn't really the derivative of the cross-section with respect to the solid angle. In reality, when we have a beam of particles hitting a target, there's going to be some separation between them, which we typically denote as something called the impact parameter. And this d sigma is usually expressed as a differential in the impact parameter. So in reality, this differential cross-section is just a ratio of the differential solid angle that the particles can scatter into and something that's proportional to the differential in the impact parameter. But it's just called the differential cross-section. Now, if the cross-section gives us some idea of the size of the object that we're hitting, the differential cross-section gives us this notion of the shape of the object. Okay, so these are the two primary things that we work with. Now the solid angle will typically also depend on phi, but when you do the integral over the solid angle, you end up getting just this factor of 2 pi anyways, so it ends up typically not also depending on phi. Or you can choose a geometry of the scattering experiment, maybe where there is no phi dependence specifically. But in general, the scattering, the solid angle will depend on phi. For what we've been considering so far, cross-sectional area giving us this notion of size and the differential cross-section giving us an idea of the shape of the object is completely appropriate when we have billiard balls colliding with each other. That stops being helpful or even right as soon as we stop being so naive and we understand that interactions actually happen at a distance. It's not billiard balls colliding, it's like siblings who are trying to annoy each other. Like, I'm not touching you, but you can still feel it, you know what I mean? So as soon as we say that these particles aren't touching, they're actually subject to some potential, some kind of like action at a distance, we can't think of these things as describing sizes and shapes of the object, because say we have two particles that are colliding that are electrically charged. They will either attract or repel. They may have, if it's two like charges, they're going to repel even though they didn't occupy the same geometric area. So in that sense, the cross-section will be larger than the cross-sectional area of what you're hitting. So we can't interpret it anymore as the size of the object. So these kinds of things we're going to delve into a lot more in the next video. We'll be interested in this differential cross-section. and we'll understand how we can relate the differential cross-section or the cross-section when we talk about real scattering experiments, scattering from a potential, in terms of the strength of the interaction. That's what you're actually probing, is the nature of the interaction. So we'll talk about that more in the next video. I know this one was very long. I'm sorry about that. I'm not quite sure how detailed I want to be in the next video because I do nuclear and particle theory, which means when I talk about cross-sections, I'd want to relate them to cross-sections as defined in nuclear and particle physics experiments or particle theory. But that can get, this was pretty conceptually difficult, I think, to relate everything. Next video can be very difficult mathematically depending on how I want to go. So I'd like your input in the comment section if you don't mind. We can go down the rabbit hole of talking about S matrices and Lorentz invariant phase space if we really wanted to, or we can just keep it simple. Maybe throw the words around so that you know what to look for in the future, but maybe not really go into it too much. So that's kind of up to you. I'll leave it up to you. But I hope you guys found this video helpful, a little bit useful. Let me know in the comment section if you did, and I'll see you guys there.